Crikey! Welcome to Honors Physics Lesson 8.2 on angular acceleration. Alright, so this section is actually going to go pretty fast note-wise, because angular acceleration is very similar to linear acceleration, but instead of using our linear velocity, we're going to use our angular velocity. So, very similar to before, linear velocity, this is how fast an object's moving over a given amount of time. Just like angular velocity is how fast something is spinning or rotating at any given time. So with acceleration, what we're going to look at is our change in our angular velocity over time. Right? Just like our linear. However, we have a nice jumper equation that allows us to go between the two, between linear and angular. And I realize that this, well, I'm very close to this when it's typed out, but this is actually the Greek letter alpha, which kind of looks like a fish, maybe a little better than that. But this is our symbol for angular acceleration, so that's our variable. Alright, I got a whole new set of equations that you need to memorize or you will fail everything. No, I'm just joking. You're not going to fail anything. And these equations actually aren't hard at all, and you don't need to memorize them. So basically what we got here is here on this side we have all of our linear quantities. So we have delta x, we have our acceleration, we have our velocity. On this side we have all the exact same equations, only now we have delta theta, we have our angular acceleration alpha, and we have our final initial angular velocity. So the equations are all the same, we're just substituting in our angular variables. So let's go ahead and give this a try. Alright, so you're on a carousel at Comerica Park. Oh man, wouldn't it be nice to go to a Tigers game right about now. But anyways, you're at the park. The carousel is going around, it's got a radius of 3.5 meters, and it gives you a maximum frequency of 0.5 hertz in 4.5 seconds. So what does all this mean? I'll tell you, it means I'm going to rule the world. No, this is giving us our maximum angular velocity. So this 0.05 hertz is actually 0.05 rotations or revolutions per second, right? Because a hertz is a vibration or cycle or rotation per second. So for every one rotation, we have 2.5. So that should give us 0.314 radians per second. That's our final angular velocity. Our initial is at rest. So to figure out our angular acceleration, we're going to take that 0.314, subtract our initial, and divide by our time, which is 4.5 seconds. And that should give us 0.07 radians per second squared. So that's our angular acceleration. Part B is asking us to figure out what angle the ride is going to turn through. So whenever we're dealing with angles with circular motion, we're looking at radians, not degrees. And we want to know how many radians it goes at once it's achieved this high speed. So to find our delta theta, we can really use any of the equations that we look that have delta theta. You could use this one, you could use this one, or you could use this one. Whatever one you want, it's kind of your choice. I'm going to go in the middle for the middle one, because I don't really use that often, so it might be fun to try. If I don't mix up the slide order every time I move. Okay, so we have delta theta. That equals half plus our initial times time. So we have 0.314 times 4.5, and that should give us our radians, our angle that we're going through, and that is 0.7 radians in that amount of time. Alright, now it's asking for our linear velocity. So if we're at the edge, what is our linear velocity going to be? So if we're at the edge, our radius is 3.5. So we can use a jumper equation. Velocity equals angular velocity times the radius. We know what our maximum angular velocity is, 0.314. We know what our radius is, 3.5. And we should use that to figure out what our linear velocity is. That should be 1.1 meters per second. Alright, let's go ahead and give this another shot. It's another practice problem. This one's a little bit longer. It can be a little bit tricky because there's a bunch of stuff that we have to go through. So first thing first, let's take anything that we see that is in our English units and convert that to metric. So 60 miles per hour, 60 miles per hour. For every 1 mile, we should have 1,609 meters. And then for every 1 hour, there are 60 minutes. And for every 1 minute, there is 60 seconds. And that should give us 26.8 meters per second. So that is our initial, right? Because we're going 60 miles per hour. Our final is 0, right? So we want to know how many times the tire rotates before it comes to a stop. Well, let's go ahead and... Ooh, I want a fun color. Let's see. Ooh, this one's like bright pink. All right. So we're looking for delta theta, right? Delta theta. So this delta theta should equal our delta x divided by our radius. So we can get our delta x directly from our linear velocity. Right? And there's a couple ways that you can go about doing that. So you can figure out the acceleration, use the acceleration and the final initial velocities to figure out delta x. You can use the acceleration and the radius to figure out your angular acceleration, and from there you can go however you want to do it. I'm really not going to be too picky. I'm just going to jump right to it, so let's go delta x equals 1/2, 26.8. I did this backwards, sorry. Plus 0 should be the other way around. Not that it matters, but if you're doing this at home, I don't want you to get messed up. Alright, times the time, which is 8 seconds, so our delta x should equal 107.3. Right, initial, final plus initial. Just don't want anything to be confusing there. Alright, so that is in meters. And if we divide that by a radius, which is 0.35, we should get how many radians we have. And that should be 306.5. But it doesn't want radians, it wants rotations. So that means we got to convert these radians into rotations. So every 1 rotation, there's 2 pi. So we got to divide by 2 pi, and that should give us 48.8 rotations before it comes to a stop. Alright, so part B. Part B is asking for our angular acceleration of our tires. So in order to do that, we should know what our linear acceleration is. We can also use this delta theta to kind of, figure that out as well. We can use this, go to final angular velocity. It really doesn't matter, whatever you feel more comfortable with. I'm just going to go use what we have. So our acceleration is linear, and that should equal 0 minus 26.8 divided by our time, and that'll give us a negative 3.33 meters per second squared, and that's our linear acceleration. Our angular acceleration should equal our linear divided by the radius. So, negative 3.3 divided by 0.35. And that should give you negative 9.58, 9.6 radians per second squared. Alright, so that's angular acceleration. Join us next time, same bat channel, same bat place. Goodbye.